This is one of my older projects, and to be honest, I'm sure that 90% of people who see it in a portfolio have no idea what's actually going on behind it. The client behind this project clearly had a strong technical background. The job description was precise, and he knew exactly what to ask for. The budget range between $8 and $25 per hour shows he understood the complexity involved. Honestly, one of the best types of clients to work with: technical, reasonable, and open to proper solutions.
He studied the problem, knew what he wanted, understood technical stuff, SMART, and he never imposed dumb solutions.
Let's take a closer look at what the client actually asked for. This is an avalanche forecast website that publishes detailed reports for 10 different regions. Each region has its own dedicated page, showing data like danger levels by elevation, avalanche problems, and more. These pages are updated daily and contain a mix of structured and visual content designed for human interpretation, not machines.
Ha for humans, not machines. Ha 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 ha.
Technically, the site loads content dynamically. Most of the data isn't rendered as static HTML. Although I was able to locate and access the internal API, it didn't provide all the necessary information. That's because a large part of the data, especially aspect, elevation, likelihood, and size, is presented using SVG graphics. These aren't simple text values. They're visual elements, styled dynamically via CSS classes and drawn directly into the page. So, instead of reading text, the program has to detect which areas are shaded or activated. For example, north-facing slopes at upper elevation. This requires interpreting the structure of the SVG itself, not just scraping HTML.
This isn't really engineer's task.
Dynamic page equals built with JavaScript, not just HTML. Data loads after the page is open gives harder to extract. If you try to view the page source, it's not there. The actual data isn't in the HTML. Instead, the data loads after the page is open through JavaScript, once the browser starts rendering it. So what you see is built in real time, not written in the page by default.
Oh, come on! Who made this?
Now, let's talk about SVGs, because this is where things get tricky. SVG stands for Scalable Vector Graphics. It's not regular text, it's a visual element, like an image built with shapes and coordinates. You can't copy and paste data from an SVG because there is no text to copy. It's just paths, circles, and styled areas. Unfortunately, many of the key data points on this website, such as aspect, elevation, likelihood, and avalanche size, cannot be copied using simple text tools. For example, aspect and elevation are displayed as SVG graphics. You can see directions like N, Ni, E, but these aren't real text. They're visual elements. Even labels like likely, which refer to the avalanche probability, are not written as regular text. They're actually embedded inside SVGs and represented by the position of graphical elements. So, to extract this kind of information, I had to read and interpret the SVG structure not as text, but as visual layers, just like a human would. Let's do a quick test. What happens if we try to copy all the text from the avalanche page? We select everything and paste it into a document or text editor. There's no aspect diagram, no elevation levels, no likelihood position, no size indicator. So even if you copy the whole page, you lose the critical info the user really needs.
Is that a picture or data? Ugh, I thought this was copy-paste, now it's science?
This is the aspect elevation diagram. It shows where the avalanche danger exists. Each wedge represents a compass direction: north, northeast, east, and so on. The vertical layers represent elevation zones. Upper elevation, 8,000 to 6,500 feet. Middle elevation, 6,500 to 5,000 feet. Lower elevation, 5,000 to 3,000 feet. The shaded zones show exactly where the problem exists. Gray means danger. White means no danger.
No, gray, nope. I'm going white. White only!
Likelihood tells us how likely an avalanche is to happen. Size tells us how big and destructive it could be.
These avalanche data points must be extracted with precision. No room for error, every detail matters. That's why we needed to build a program that, once launched, consistently delivers all the critical data, perfectly structured and 100% accurate, every single time.
How the program works? The tool was built using Selenium, a powerful browser automation framework. First, we programmed Selenium to load all 10 forecast pages, wait until each one was fully loaded, and scroll down to the bottom to ensure all dynamic content is visible. Then, for each page, the full text content was saved. A full-page PNG screenshot was captured at high resolution. Next, the script parsed all the embedded SVG elements, extracting both the textual data and the visual elevation aspect zones. Each element was saved with its corresponding context, allowing us to trace exactly which region, problem, and zone it belongs to. In this stage, the script did 3 essential things. So, what does our program actually do? Using Selenium, we tell it step-by-step what to do. 1. Open each forecast page. 2. Wait until the dynamic content is fully loaded. 3. Scroll all the way down to trigger everything. 4. Adjust resolution to make sure the entire page is visible. 5. Select all the text and save it. 6. Take a full PNG screenshot. 7. Then extract every embedded SVG. Sometimes there are 2 or even 3 per page. All this data is saved in a clear, organized structure ready for the next stage of parsing.
Wait a minute. So the page loads, and then the little thingies go into the big graphic thingy. Oh boy, this is some next-level engineer mumbo-jumbo.
At this point, we now have everything we need: aspect and elevation data, full text content, and a full-size PNG screenshot for visual validation. This image allows us to visually verify that all data was captured correctly. Later, using regex patterns, we can format and structure the raw text into clean, reliable data, fully aligned with what's shown on the page.
Regex, Mambo-Nambo #1.
Finally, we also need to extract 2 critical indicators: likelihood, which represents the probability of an avalanche occurring, and size, which tells us how large or destructive that avalanche could be. These values are not written as plain text on the page. Instead, they are displayed inside SVG graphics, meaning we had to locate and decode their visual representation programmatically with precision. Let's see what the program actually does.
Well, look who's here.
Shut up for a second.
Andre Soren is in the house.
Oh no, serious stuff.
Yeah, it's called automation. Try not to break it.
It loads the avalanche forecast page, scrolls to the bottom, ensures full resolution, selects all visible text, saves it, takes a screenshot, extracts every SVG, and maps every value with precision. After completing all those steps, the program launches a second script, and this one is responsible for the final data organization.
For detecting and interpreting the likelihood and size values, the program dives deeper. It opens each page and directly inspects the page source, more specifically, the SVG elements, to check which values are active. It analyzes each SVG component to detect which values are currently active based on class names, styles, or fill attributes that indicate selection. Only the activated values, like selected likelihood or size levels, are extracted and saved into a clean, structured JSON dictionary.
Because some pages may contain multiple identical values, such as 2 or even 3, size or likelihood indicators, the program uses a more advanced method to determine which one is relevant. It measures the pixel distance between SVG elements based on their position on the page image, allowing it to correctly identify whether the active value belongs to the first, second, or even third section.
It's not random. It's 1, 2, 3, dude.
In this way, we can correctly interpret the size values as well, even when one or two values are present on the same page. The script identifies the position of each element based on pixel distance and saves them in the right order. 1, 2, and sometimes 3.
But wait, are those pixel distances in 4000 resolution or like ... HD resolution? Because that could totally be relative, dude.
Pixels taste the same in 4K.
Another key function of the program is the interpretation of SVG graphics. It reads each SVG zone and analyzes the color values specifically to detect the shaded gray zones. Gray means danger, interpreted as true. White means safe, interpreted as false.
Wait, so this gray stuff means danger, and the white stuff means snack break?
So, now, we have all the elements correctly saved. The text, the elevation zones, the likelihood, and size. Everything. The only thing left is for the program to organize this data properly, so we get the final result structured, accurate, and ready to use.
At some point, I thought this was Ninja Doctor engineering stuff. But, hey, it's not that complicated. Just dangerous snow and scary SVGs.
Although this is a dynamic site, it does not have strong protection mechanisms. The data is loaded all at once. There's no need for form, submissions, or navigating through multiple steps. Unlike other platforms where you have to click buttons or wait for content to load progressively, this one presents everything in a single structured load that simplifies some parts of the automation, but challenges still exist in extracting SVG-based visual data accurately.
This project was completed by me, Andrei Sorin. I wanted to take a moment to explain it in detail because, at first glance, it may seem simple. But the truth is, behind every clean output, there's a precise and carefully engineered solution. Automation like this requires not just coding skills, but the ability to understand structure, logic, and the data's behavior. I believe it's important to show the thinking behind the code, and I hope this breakdown offered some insight into that process. I have over 7 years of hands-on experience with Python, focusing on high-level automation, data processing, and system integration. My work combines strong logic with precision and real-world efficiency, always aiming to build tools that solve complex problems reliably.
Oh, I think this guy is really good. Like, dangerously good. Like, eat a donut while coding good.
Yeah. Calm down, Homer. There are better ones out there. Don't get emotional. He's just ... like, top 1% or whatever.
Wait, there are people better than this guy. What? That's not even legal.
Relax, Homer. He's good. Sure, but there's always someone better. It's called reality, dude.
Thanks for watching. See you next time with another project.